This problem presents us with a tapered beam that is fixed on the left side and free on the right side, and we are interested in finding the natural frequencies, the first four natural frequencies of this beam when it's in transverse oscillations. So we want to find omega 1 through omega 4. Unlike the previous two examples we looked at, we don't have an analytical solution for this one that we're going to be able to compare the finite element results to, because if we look at this, the area and the area moment of inertia are not constant as we go from the left side of the beam to the right side of the beam, meaning we cannot make some of those simplifications required for the PDE equation of motion that we had from the analytic section. So this falls outside of that scope. So we're going to need to come up with other ways to validate the answer we get from the FEA to check if it's at least a reasonable value that we get for the first four natural frequencies. So we're going to proceed in a similar way than how we did this to the axial problem. That one, though, was a fixed beam. That's not a big difference, but how we're going to think about the modeling step or the meshing step for this. So on the left, we have this fixed wall. And what we're going to do, since we have this linear taper here, or if we had any sort of taper, we have the rule that in our element, for finite element analysis, each of the elements must have a constant A, E, I, and rho. So what we're going to be able to do, I'll just illustrate here with three elements. So we have this very kind of coarse-grained mesh here, so it's a very blocky descent. But what's going to happen as I keep adding more elements into this system, and the elements are getting thinner and thinner and thinner, is I keep adding more, and what we're going to see is that as we go from one element to the next, we're going to have a much smaller step change in the cross-sectional area and the area moment of inertia, because the radius is going to be changing more rapidly. So I won't keep drawing them, but that's what would be happening. It's going to be much smoother transition and more approximate better the taper we're going to see. In this case, that linear taper. But for starting out, so it's easier to draw and less to draw, if we only had three elements here, we're going to have a W1 and W2 for the position and angle of that first node, and a W3, W4, a 5 and 6, and 7 and 8 for the last one. And similar to how we did this for the axial version of the problem, we have some choices to make about how we are going to determine here the cross-sectional area and the area moment of inertia for each of these elements, because we have to have it constant in the element itself, and that can change as we go to the next element. For the axial version of this, we had three more obvious ways we could approximate what the, let's say, the radius and therefore what the area and the area moment of inertia was going to be. We could say that each element is going to have the radius at the left node, or we could say that each element would have the radius as calculated on the right node, or we can use the average radius, I'll call it R bar here, which will be the average of the radius on the left and the radius on the right, and use that value to calculate our moment of inertia and our cross-sectional area. Like in the axial problem, no matter which of those three at least definitions we use, as we keep adding more and more elements, there's going to be such a small difference between the radius at the left and the radius at the right that they're all going to converge to that same value. But what we could see happening is that we are going to start overestimating all of the natural frequencies versus underestimating all the natural frequencies. So the direction of that convergence could change. Are we coming in from above or below? But since we're seeking convergence, we're really just caring about where does it flatline, and that's going to be the value we're using for our natural frequencies. But just be aware of that difference in how we're defining the radius, the constant radius for each of the elements will change how it converges, but in the limit of an infinite number of elements should not impact what it actually converges to. So determining that mean radius we're going to have to do for each of the elements, as again A and I will change as we go from element 1 to 2 to 3 and so on. And what we have here for our boundary conditions is W1 is always going to be 0 and W2 is always going to be 0, like the previous fixed free that we saw. That always, as I define the elements, even as they increase, 1 and 2 are always going to be attached to the wall. The free end is going to change, but we have no boundary conditions to enforce there. So in the global stiffness and mass matrices, I will be eliminating the first and second row, first and second column, in order to enforce these boundary conditions. So looking in the code here, I will be tracking the first 4 natural frequencies in this example. And I'm going to go from using only 3 elements to using 300 elements and making sure that it does converge by the time I reach that upper limit of 300 elements. If I don't see convergence, I can always go back and add more of those elements until I get convergence. Okay, so I'm going to define here my left radius and my right radius, and we'll see I'll be modifying those a bit later. But in this original problem, we were told the diameter on the left was 0.4, the radius on the right was 0.1. So I'm just converting them to radii so that I can use those radii to compute my area and my moment of inertia. Then I go into basically the same loop I've been using for these transverse problems, where I am going to keep upping the number of elements that I'm using in my finite element model as I go, so I can track the convergence. And I'm going to make that map list, since I have those 2 degrees of freedom on the left and 2 on the right for each of my elements. So the one new thing that I have to modify here, and this looks like what we did in the axial version of this, is I am going to come up with the radius at each of those nodes as they are evenly spaced across my element. So that's what I'm doing here, is I'm finding the x position first of each of the nodes that I've established, which is going to be dependent on the number of elements I'm using. And then I know what the radius at each of those nodes should be, since I have this linear taper in this particular problem. Now, if I had nonlinear taper, I can still do the same step. It's just how I'm going to calculate my radii will be different depending on how is this bar tapering. Is it quadratic? Is it exponential? In this case, it's just linear. So let me go for j equals 1 so that I can see what does this look like when I have the 3 elements like I had in the picture. So let me just run everything up to that point. So when I have just the 3 elements, I'm going to have those 8 degrees of freedom like we've seen before, and I can look at our list, and what this is showing me is what's the radius at each of those nodes. So this is the wall is 0.2, and then at the free end it's going to be this 0.05, which we should expect, and then the 2 nodes that are in between are just going to be that linear decline in the value of my radius. So then what I'm using here is I'm calling it R mean. I'm going to use the mean radius for the radius of each element. So for element 1, I'm going to take the average of, again, the left radius and the right radius at those nodes. For element 2, I'm going to take the average of these 2 values, and for element 3, the average of these 2, and use that then to calculate area and moment of inertia. And that's what I'm doing here as I go element by element and I calculate their local stiffness and local mass matrices. For each element, I'm computing its A and its I that is going to be constant the whole way through. So that's what I'm doing in 42, 43, and use those values in for my local stiffness, local mass matrices, for here the I, and for the A in my mass matrix. Then just like before, I put them into the global matrix in the correct spot. So what is going to be different in this problem than the first 2 is now my local stiffness and mass matrices change as I go from the left element to the right element, because the A and the I are going to change as I go from the left to the right. So this is what prevents us from getting an analytic solution, at least using the methods that were discussed in the previous section, that A and I not being constant, we cannot do analytically the same way we have been doing the problems where A and I were constant. Then I can apply my boundary conditions for all of these iterations. For no matter how many elements I have, the first 2 rows, first 2 columns get eliminated to enforce that position is 0 or deflection is 0 at the wall, and the slope at the wall is 0. So no matter how many elements I have, that's going to look the same. Then I can find my 4 smallest eigenvalues. square root them, and those are going to be my first 4 natural frequencies, and I'm going to track them as I keep adding more elements. So again, really the only real change between this and some of the previous ones that we did is that A and I change per element as I go left to right. So let's see what happens as I track these 4 natural frequencies and I keep adding elements into my system. And if I look at convergence here, once again, I don't know now up front what the answers should be. I don't have the analytic solution for this problem. But what I can look at is, first, do my values converge? If I go here, from bottom to the top are my first 4 natural frequencies, and these are the actual values of them. I'm not dividing them by the true answer, because I don't know the true answer in this case. But I'm still getting that same trend that they are converging to some value. So what I'm going to need to do is get some assurance or some confirmation that the values I'm finding are hopefully the correct ones, and I'll do that by a couple of different means here. So if I look, they all are flat by the time I'm at 200 elements, so I'll just use their values at 200 elements for now. So we see the first natural frequency, I am getting a value of about 735 radians per second, and then 2300 for the second, 5200 for the third, and 9500 about for the fourth, the highest natural frequency. So all of them have converged, they have all gone flat. Now I want to back up these results before I necessarily accept these as being the first 4 natural frequencies in my system. So one way I can maybe bound my answer or get a ballpark magnitude of what these values should be is I could simplify the system into one that I am able to solve by hand. So what I would be able to do is, instead of treating it as a tapered beam, I could get maybe a rough idea of what the values should be if instead I treated it as a beam with a constant diameter. And I could do that 2 different ways. I could say it's all the constant diameter of 0.4 meters all the way from left to right, and now it's a system I can solve analytically. I can get the exact solution to an approximation of the problem. If I get rid of the difficult part, the taper, I can find it analytically. Also, I could say that the whole diameter is the small diameter of 0.1, and again be able to solve it analytically, but now with everything having that reduced area moment of inertia, and get an estimate of what I should get for the tapered beam with that analytic solution. I can do that not only analytically, but I could also do that with the finite element analysis, because we've shown, at least in the first example, that if we have a fixed free beam with a constant diameter, our values from the FEA did converge to the true values. So we do have a basis to say that even the FEA for a non-tapered beam is seemingly reliable and matches what we get analytically. Now, this is a slightly different beam than we had the first time, but we're going to should be getting reliable results. So from the FEA, let's just look at some quick results if we treat this as having a constant radius, a constant diameter. So I'm going to change this and say that the radius on the left and the radius on the right are all the same, that there is no taper in this beam, it's a constant radius. And if I run this and I look at my convergence, I'm getting here certainly different results than before, and I can track what these are. So this was saying that the entire beam was the larger diameter, and we can see what the natural frequencies are for that beam. Again, we should not expect them necessarily to match the tapered beam, and in fact they don't in this case. We're getting that the smallest natural frequency is 444, the Y value, and the largest is a little bit more than 15,000 radians per second, and then we get 2 in between. So certainly different than we got from treating as a tapered beam in the finite element analysis. Now, to get another estimate as to around what the natural frequencies could be, I'm going to make everything the smaller radius. So the left and the right, no taper in the beam, it's all the smaller radius, the smaller diameter. And if I run this and I look at the convergence here, again, I'm going to get, in this case, different results. And I'll just look at the smallest and the largest. Largest natural frequency, we get about 3,800. And for the smallest natural frequency, 111 radians per second. So the transverse beam is affected by the diameter of the beam even when it's uniform. If we think back to the axial problem, it actually turned out that the cross-sectional area didn't factor into the natural frequency because that A value was not anywhere in the calculation. But the transverse beam it is, because A comes up and I comes in when we are using that, well, at minimum using that C value, that C squared value to calculate our natural frequencies. So we're getting 3 different results this way, with the taper, with everything as the small diameter, and everything as the large diameter. So let's pull it all together to make an assessment of, can we trust the results we got when we put the taper in for the FEA? And let me just rerun that original one more time here. So this is with the taper and with the FEA. These are the results we're trying to validate here to see, do they seem like they are any good? Again, highest natural frequency of the 4, 9460, and the lowest, the first natural frequency, at 735. So I've compiled the results I got from the FEAs with no taper, but everything at either the large radius or everything at the small radius, what we got with the taper, and I ran these through with the analytic approach because we can, for no taper in the beam, get the analytical version using the techniques from the previous section. So just for comparison, I put those in as well. And what we see is, let's say that we have no taper, but only the large radius. The analytic and the FEA versions are in agreement for the most part. We could have probably run a little bit more FEA, and also with the analytic, keep in mind that I am using those beta values that have a little bit of imprecision in them. But more or less, everything the large diameter or large radius agrees with the analytic and the FEA method. Same is true with no taper, but everything is the smaller radius. The analytic and the FEA are in agreement. And then we have what we got here where we do take into account that taper. So let's see where our results lie. With no tapering, large diameter or small diameter, we're getting that the first natural frequency is actually lower than what we get when there is a taper in the beam. So that we should not necessarily expect it to be in between, just because with the tapering, kind of our average radius is in between the 0.2 and the 0.05. Things can happen. There's nonlinearities in the calculations here that make it that we're actually getting a higher natural frequency with the taper than without. But we see that for like the second natural frequency, in this case, we're getting a natural frequency that is between what we would think is kind of the larger estimate and the smaller estimate based on no taper. Same idea for the third natural frequency, it is in between, and actually the fourth natural frequency is at least in between our estimates from the everything a small radius, everything a large radius. So we did demonstrate convergence, which is, if that wasn't demonstrated, then definitely we should not be trusting our results. And we're getting what maybe is a kind of a strange result, that we get a higher first natural frequency than without a taper. Everything else is in between. But if we look at the order of magnitude, at least, we have 3 digits with no taper for the large radius, 3 digits for the small, and we're still at 3 digits when we have a taper. So that's telling us that this result we're getting is at least not wildly off. If we were getting something in the 4 digits or 5 digits, then we might want to question it. Now, again, unfortunately, we are only getting a rough validation here. Is our result from the finite element correct? We really don't know. We can't necessarily show this is correct, but we can have some confidence in kind of trying to get an upper and a lower limit, or at least a magnitude estimate based on the analytic solution, which was the exact solution to an approximation of the problem, which matched the FEA version of that approximation to the problem as well. So in the end, these would be our first 4 natural frequencies in radians per second for this tapered beam, and we have some confidence that these are the correct natural frequencies.